Well, I'm a civil engineer from Brazil, São Paulo, structural engineer. I have a company there that does these rehabilitation jobs in Brazil. So I'm honored to be here in the session dedicated to Mike. And I'd like to thank you, Mike, for the invitation, of course. And I'm going to talk about this rehabilitation of this bridge. It's located in the southeast part of Brazil, on the coast. Got it. The southeast part of Brazil, near, in the coast of São Paulo. It's in a connection between the continent and the island itself. There's a photo from the region. And this city, São Vicente, was the first settled city by the Portuguese in Brazil in 1532. As the city developed, it started to install a sewage collection system. So the bridge, the original purpose of this bridge was to transport the sewage between the island of São Vicente Santos to the mainland. The bridge was designed and manufactured by August Klon, which is the Krupp company now in Dortmund, Germany. And the construction of the bridge took place from 1911 until the 1914. That's the original blueprints of the bridge, in German, English, and Portuguese, of course. And that's the final part of the bridge. You can see the bridge itself. It's a steel deck, and the tower. Well, the tower itself, it's a steel truss also, and that's the inauguration photo. And the tower, you can see that were covered by concrete. They don't have any technology the best technology on the beginning of the century was to protect steel was concrete. So that's why they did it. And this bridge was listed in the historical heritage site in 1982. Well, the main characteristic of this bridge, the main span is 180 meters, 60 feet, more or less, 20 feet long width. They have lateral trusses with height of 3.7 meters, 12 feet, divided in 30 modules of 6 meters each, 20 feet. And the main support system was formed by 80 cables in each side of the deck, with 81 to 63 millimeters diameter. As I say, the towers itself was formed by steel truss and was protected by concrete. You can see on the left photo, the orange is like a coat that they took place in the steel, and it was original. It's 100 years old coating, and it was protected by concrete. And that's the main part of this bridge that to change the cables. It was the tricky part because the cables itself, the original ones, was inside the anchor block. So we have to change everything on this anchor block. That's a drawing, that's a blueprint that we did. So it shows that the main cables were connected on the back part of the anchor block. So the bridge condition in 2012, it was very bad. Like Dr. Johan, we have the same problem here. Not because of the icing, but because of the sea, of course. So we have a lot of corrosion on this bridge, on the steel elements. Also, in the support system, as you can see, loss of some section, and also on the towers we have some cracks, and also on the main anchor block. So we have to change and reinforce everything. We are going to focus on the concrete part, of course. So we have to change the concept of cable substitution. We did a provisional bridge, provisional suspension bridge, besides the original one, to transfer the load from the original to the provisional, repair everything, even the deck and the blocks, and then redo the transfer for the provisional to the permanent one. So we have to do it, and we have to do the job to the temporary anchorage besides the original one, and that's the main scheme of the transfer load, which the main reference were the towers and the main deck. So we have to keep the balance between the back part and the span part of the bridge during the transfer loads. That's the transfer load picture of that. We are transferring from the original to the provisional. Then that's the best part of the concrete. We are dealing with 100 years old concrete, so we have to demolish the main core of the block. As you can see, the original cables, and they stay there. You can see some stains, orange stains. That's the original coating of the cable, protected by concrete. So in the back part, we can see a reaction beam that the original cables were connected. So we have to reinforce that beam, and also to reinforce the core of the main anchor block with pre-stressed concrete and rebars to transfer the load from the back part to the up part, and to connect new cable support system. That's a video. So we use a lot of different as the part was that's the new cable system. It's a full locked cable, full locked coil cable. It was bring like this. Then we just pull off all over the bridge, and then we connect to the new block anchor system. And again, we have to do the transfer load from the provisional system to the permanent one, and that's the end of the job. Okay, so during all these jobs, we have to monitor everything about it to avoid any surprise, anything about during the loading transfer, and of course all the reinforcement parts that we did on this bridge. We installed some string gauges, a lot of to monitor tension, and of course the deck itself, to avoid anything during the job. The job numbers, we have some 44 tons of steel elements, new steel elements. The new system is about 120 tons, and about concrete, 800 cubic meters is about 100 cubic yards of pure concrete in the new massive anchor block. And for the final, we have to do a load test on this bridge to get rehabilitated and approved for the government. That's the load test, during the load test, and that's the reopening picture of this bridge. Well, thank you very much. Appreciate it.